Hey, what's up guys, my name is thecherno and welcome to episode 4 of the Serialization mini-series. So today we're going to be talking about binary and particularly bitwise operators and whatnot. So this is a very important episode for things to come, and it's also more of a standalone episode as well. So this is going to apply to all of you who don't understand bitwise operators and who want to and who need to. It's a very important part of programming that everyone should really know. And it will make your life a lot easier in many circumstances, but it's definitely needed for something like serialization, because right now we're dealing with converting things to and from binary, okay? And doing so requires bitwise operators most of the time, okay? So we're going to just cover all of them. We're going to see some examples and whatnot, and hopefully you'll be able to understand them perfectly by the end of this video. All right, let's get right into it. So the first of the operators that we have, right, that I want to talk about is the AND operator, the bitwise AND operator, and the bitwise OR operator. So AND is shown as an ampersand, which I'm just going to draw like that. And then the OR is just a pipe, okay? So it's just a straight line. So let's talk about AND real quick. This is basically like a kind of logical AND, right? So when you have two states, let's just say one is true and one is false. Remember, this is binary, so you only have ones and zeros to deal with. So if you have these, obviously if you had a just a normal if statement that said something like if true and false, the result would be false, right? Because they need to both be true if there's an AND there, because the AND says that if like A and B are true, then you've got your result, right? So it's exactly the same thing with binary. If you do something like 1 and 0, obviously that's going to give you 0, okay? If you try and 1 and 1 together, you're going to get 1, okay? 0 and 0 are obviously going to give you 0 because they're both false. And finally, 0 and 1 is going to be the same as 1 and 0 and just give you 0, okay? So really both of the sides of the equation need to be the same pretty much, or true, in order to get a true result, okay? So the applications of this are going to come to light soon. I'm just getting the basic explanations out of the way. OR is kind of almost the opposite, where it's essentially like an OR in a normal logical if statement, right? Where you have something like 1 or 0, of course, will be 1, because either of these have to be true for the result to be true, okay? 1 or 1 is also going to be correctly 1, okay? 0 or 0, well in this case really you can't make a 1 out of nothing. So this is going to be 0 because both of them are false, right? And finally 0 or 1 of course is going to be 1 as well. So you can see that we get much more 1s here. Whereas in AND, they both have to be true. In here only one side of the equation, or one side of the statement has to be true. Okay, cool. So that's AND and OR. There are also some other operations that we don't really need to look at. I don't think we'll be using it in this series, but we'll cover them anyway. We've got XOR or XOR and NOT, okay? So this in Java looks like a little hat, and in most languages as well, and a squiggly line, or a flail as I like to call it, but it's like a tilde, is for NOT, okay? So what does this mean and how does this work? Well, XOR is kind of so let's draw this up. XOR is kind of like OR, except with one big difference, okay? So XOR actually stands for exclusive OR, okay? So it means that one of these has to be true, but not both of them, okay? So the way we can do that is say that if either of these are true, which you can see only one of them is true, right? Not either of these. So either of these would be OR. One of these, exactly one of these, would be XOR, right? So because one of these is unique, essentially, because one of these is 1 but the other one isn't, this returns a true result, okay? So basically the only difference from the OR is if we have something like 1 XOR 1, that's going to give us 0 because then they're the same. Okay, so 0 or 0 is also going to give us 0, of course, and 0 or 1 is going to give us 1. Okay, so you can see it's like OR, but the 1 or 1 is replaced with a 0 result. Not is something that works on, that isn't really part of an equation. It's more or less something that you pass into a number. What I mean by that is that typically you can't do something like 1 not 1 or something. That doesn't make any sense. So you just stick it in front of something. So like not 0 and not 1. So what this will do is it will basically reverse. It'll invert the bits. Okay, so the number that you get from here highly depends on how big your number is in terms of how many bits are in the number. Because when I say something like this, right, the number might be, if we're dealing with like an integer, it's going to be 32 bits, right? So if you invert 0, you're going to get the 32-bit version of just ones, right? So in this case, if we're just dealing with a 1-bit number, this of course will give us 1 and this will give us 0, okay? So it just inverts it. Again, not something that's particularly useful for this. It is generally quite a useful operation. It's great for like flipping states and flipping flags and whatnot when you're trying to deal with bit fields. I've certainly used it for that, and it's been pretty useful. But yeah, we probably don't need to look at it too much in depth. These two, though, we will look at some real-world applications and whatnot. Okay, the final thing you really need to know is something called bit shifting. Okay, so bit shifting, we have two operators for that. We've got the left shift and we've got the right shift. Okay, these are again very simple. All they do is shift the binary value a select number of places. Okay, so if we have something like 0, 1, 0, 0 in binary, which of course would be the number 4, if we've got something like this and we decide to shift it left one spot, essentially, that's going to give us 1, 0, 0, 0. Because you can see we've literally taken this guy and we've just shifted it one place to the left. Okay, this place is always in bits, of course, not bytes or anything. So if you want to shift it 1 byte, you just write 8 over here. Okay, this is kind of the other way around. If we had the number 4 and we decided to shift it right 1 space, we wind up with 0, 0, 1, 0. So you can see it's shifted right 1 space. Now, if you were clever enough, you probably would have noticed that this was 4, right? And it became 8 when we shifted it. And then when this was 4, it became 2 when we shifted it right. Okay, so left shifts at 8, right shifts at 2. So you can probably see that the number actually doubled when we shifted it left, and it halved when we shifted it right. Okay? Now, that in mind, you can actually convert this bit shift into just a normal mathematical operation, right? And all this is really is a number such as 4, yeah? And all you're doing is, in this case, in terms of a left shift, you're actually multiplying it, right, by 2 to the power of the number of places that you're moving it. So 2 to the power of 1 in this case. Okay, so multiplying it by 2 to the power of 1 results in it being 8, of course. And in this case, you're doing the same thing except dividing instead of multiplying. So in this case, it's going to be 4 divided by 2 to the power of 1. Okay, so 4 divided by 2 in that case will be 2. Okay, so you can actually do this with normal maths. You don't need to do this in binary. In fact, you can only do it in binary if you're basically operating on integers. Of course, there's no such thing. You can't do this to like a float or something. But this is typically usually more readable if you're actually dealing with binary operations. And if you're dealing with something like color, for example, and you're extracting channels, and we'll talk about that because that's a great example of binary. Then and you want to shift left by like 24 places, obviously, you know, instead of that, if you wrote multiplied by 2 to the power of 24, that would be a huge number. That's just not going to look too clean. So anyway, that's what bit shifting does. Very simple. It just shifts the bits. Like if you had more complicated examples like this, for example, and you decided to shift that left 3 places, for example, that would kind of overflow in this case. But if your integer was big enough to store it, then it would look something like you might have 1, 1, 0, 0, 0, right? So you would shift it left 3 spaces and you would wind up with whatever you get, okay? Similarly, if you try and continue shifting it right, you'll eventually just hit 0, okay? Because you will run out of places. So anyway, that's how that works. it's pretty simple, honestly, and it's really not anything that you guys probably couldn't have understood if you just looked it up, because it's really quite simple and it doesn't take too much time to learn. Now, where I see most of these videos failing is in explaining how this is useful, because it's great knowing that, oh yeah, I know how this works, so if I see this in code, I can recognize what it does and I can, work it out. Yeah, sure, that's not really particularly difficult to do, is it? The problem comes from, hey, how can I use this, and why would I even want to use this anywhere? Okay, so that's what we're actually going to talk about right now, because it's very important to cover that. So we're actually going to do some programming finally. So this is the deal, right? The first thing I'm going to write is a function called print. Okay, and this is going to take in like a number essentially. And I'm going to output it in a special way. I'm going to output it as a printf, okay? And then I'm going to set the format to be hexadecimal. All right, that's all I'm doing. So the reason I'm doing this is because it's a great way for us to just quickly print something as hex. And of course, this is going to be a void method. All right? Now, you can actually print stuff in binary as well. So I might do something like private static void print bin or something. And then this will just do a normal system.out.println, but it will do integer dot to binary string value. All right, so this way we can now print both hexadecimal and binary if we need to. Okay, and you can change this to like print hex. All right, cool. So let's get right on into this. So the first thing we learned about was ANDing, and we'll talk about how that can be useful. So if we have a value, for example, one thing I should mention is this is much easier to do if you're actually in hexadecimal land, because if you're in hexadecimal land, then each digit is 4 bits, of course, and it kind of all lines up nicely because you know what you're doing. If you kind of start writing values like 255 instead of FF, then you're going to run into trouble. Anyway, suppose we have a value such as we've got like a color, for example. Or let's just say we've got 1234. Like I said, this is our footer. Okay, so right now this is quite a large value. If we tried to print it or something as a normal decimal, we would get something like 4660, right? If we print it as a hex, then of course we should expect to get the exact same thing that we entered. And there you go. However, what if we wanted to, for example, extract part of this? So you can see that this is 2 bytes, yeah? It would be pretty useful for us to maybe split this up into 2 actual byte values, okay? Because if we're outputting it, for example, into, I don't know, just into a file, and we want to precisely write the bytes or something, we might want to split this up into 2 bytes, for example. So how can we do that? Well, a good way to do this is by using bitwise operators. Okay, so this is where ANDing and shifting comes into play. So the first thing we can do to it is we can actually use the AND operator to extract parts of it. So I'll call this variable A, and essentially it will be our value, okay, and 0xff. Okay, so what I'm doing is I'm ANDing this by essentially a full set of bits. So if we go back to the drawing board for a second, and suppose we have like FF essentially, which is equal to 255, in binary is expressed as 1, 2, 3, 4, 5, 6, 7, 8 bits. Okay, so it's a full byte of ones. Now we've learned that by ANDing anything by 1 is really the only reason, by the way. If you AND anything by 1, you will get 1, okay? Which means that if we have a number that's just 10101010, for example, and we AND this by a series of ones, like that, then the result we will get in this case is actually just this top number, okay? Because ANDing anything by 1 will give you basically the original result. So 1 and 1 is going to be 1, 0 and 1 is going to be 0, and it's going to kind of continue like this. And there you go, right? We've got that same number we had up the top in the result. Okay? So this is what's called a mask as well. It's called a mask because it lets us kind of select a region of numbers. Because let's just say that we wanted to select a particular region of this number. For example, we just wanted the bottom bytes, or the bottom bits rather. So what we could do is, if we had this long number and we just wanted to select this region, we could AND it by 00001111, which would mean the result we would get, obviously this is all going to result in 0, which just cancels out, right, because it's all 0. And then of course this will give us 1010. Okay, this is what bit masking is. It's very useful because it lets us select essentially regions of bits and discard other bits. Okay, so cool. In this case, if we were to print something like this, and again we're ANDing this number by FF, we would get something like well, like that first involves us actually printing the number. We would get something like 34. So you can see we've managed to extract this bit, which is pretty cool, right? Because what we've essentially done, a better way to write this might be something like 00FF, which doesn't actually do anything, but it kind of helps us. You can see that we've got this number, and essentially we have ANDed it by this number, okay? And you can see that now I've kind of got the digits lining up. These two things kind of cancel out because they get ANDed with 0, just like I showed you in our example over here. And then in this case, the FF, of course, means it's just a full bit of 1. So whatever is here will just get pushed down, and that'll be our result, which is what our result is. Okay? Pretty cool. Now, we've managed to extract this part of the number, but how do we extract this part of the number? That's the question, right? It's actually not that simple, because if we try and do something like FF00, which is what you would logically think, we would get 1200 in hex rather than just 12, because we really just want 12, right? And that's because, of course, by ANDing it, we're kind of reducing this to 0, but since the digits we want are basically followed by a bunch of zeros, right? They're in front of a bunch of zeros. Those zeros actually mean something. When we have like leading zeros, they don't mean anything. We're going to have a million zeros in our number, and the number is still going to be 1200, right? However, when we have trailing zeros, they obviously increase our number. Okay, so there we go. That's our number. How do we just get the 12? And that's where bit shifting comes into play. So imagine you had this scenario, but the other way around. So we had 10101010, and we ANDed it by 1111 and then 0000, right? This would give us 1010 with a bunch of zeros, which is basically what we've ended up with. So what we really want to do is take this and we want to shift it that way, okay? So in this case, if you count it, 1, 2, 3, 4, we need to shift it 4 bits to the left, sorry, to the right, right? So we shifted 4 bits to the right, and that, of course, if we do something like that, then we will end up with 1010, and that's it. Okay, done, because this entire thing will move 4 bits. So, that being said, let's do that. So if we had something like this, in this case we actually have to move it 8 bits because this is like a full byte. But if we do something like this, so if we were to AND it by that, and then shift it right 8 bits, then the value that we would get would be just 12. There you go. Alright, pretty cool. So you'll see this stuff all the time in stuff like color, for example. So if we had a color, and one of my favorite colors is pink. So this is what pink looks like. Each byte here, this is a 24-bit color. Each byte here is a separate color channel. So obviously this is dependent on how you interpret the color, but in this case, we've got RGB, where the first two digits here, or the first byte, is the most significant byte is red. The middle byte here is green, and then the least significant byte is blue. All right, so we've got a color here, and then I might want to extract this in terms of RGB, right? I want to have 3 separate variables that are RGB. So how can I do that? Well, I would encourage you guys to have a go right now before I do, and just test out, because everything I taught you right now should apply to this. So I'll give you a minute. Now that you're hopefully done, pause the video, have a go, and let's take a look at the answer. So red, okay, will be something along the lines of color and 0xFF0000. So we're selecting just this part here. So now this result right now would give us that, because we're ANDing this entire thing by this, right? Now we need to shift it right. So we shift it right 16 bits. Okay, and that winds up with being over here. All right. G, or green, is going to be pretty much the same, except we're going to end it by that, and then we're going to shift it only 8 places. And then blue finally is going to be pretty simple. It's just going to be color and FF like that, shifted nowhere. Okay, so you can write that, which of course translates into divided by 2 to the power of 0, which of course equals just divided by 1, because 2 to the power of 0 is 1, which would be nothing. So you can leave that there if you like, or you can get rid of it. Okay, so now that we've got this, if we were to print R, that's not going to work, RGB, then we would get into, we would get FF00 and FF. Okay, so 255, 0, 255. There we go. So we've separated this color into a bunch of integers. Pretty awesome stuff. So now let's talk about how we can actually reassemble that color. So how can we do the reverse of what we just did? We managed to extract this, but how do we put it back into what it was, right? That's also something useful. So for example, in this case, let's just say that we had a number and we were trying to like reduce its brightness or something. So we decided to do something like, once we had the channels, we subtracted like, I don't know, 10 from it or something, okay? This will give us a negative number in this case. So pretend that we just had it like a check here that said if green was less than 0, green equals 0 or something like that. So we won't do anything for that. But let's just say we did something like this, right? And then we wanted to reassemble the color, obviously, because we wanted it in this format again, in a single integer. So how can we do that? Well, this involves basically the reverse of this. So this is where our ORing situation comes into practice. So this is where we use OR, and we also need to use a left bit shift. So those are the two things we'll be using. So the first thing we need to do is actually shift that color back into place, or that value back into place. So it needs to be where it was before, okay? The way we can do that is just simply by taking something like, so if we have our result here, we can take something like the R variable and then shift it left 16 places. That puts it back into place. So if we were to print something like this, we would get CD and then a bunch of values. So CD, because we've of course reduced it by 50. If we didn't do that, we would get our normal FF, but you can see it's followed by a bunch of zeros. Cool, so we're kind of done here. But then, wait, we also want these bits to be whatever green is. So let's just for lols here, let's increase green by like 10 or something. So that's just so that it's not, or even something like, I don't know, 28. So that it's not just 0, 0. If we have something like this, how do we also put the green into this variable? Because right, this is an integer, so we can actually store something in this byte, and we can store something in this byte. So how do we do that? That's where the OR comes into place. Okay, so back to the drawing board. What we're doing now is essentially we've wound up with a number such as FF, and then you can see we've got a bunch of zeros at the end here. Okay, so if I were to expand this, it would be essentially 16 ones followed by 32 zeros, right? Which we're not really interested in drawing. I don't want to draw that many digits, but basically the idea with this is that once we've got something like this and we want to combine it with something like, for example, the thing we want to really combine it with is like, let's just pretend it's FF 0, 0, and we'll just put zeros here just for the sake of lining up, right? We just want to combine these, and we really want to get FF 0, 0, right? How can we do that? Well, it's very simple, because we can do that with the OR operator, okay? Obviously, if we have something like, if we broke this down into binary, just so you guys can see, and we had something really simple like that, yeah, we know from these rules that 1 or 0 is still 1, okay? So we can combine sections of numbers essentially by using the OR operator, okay? So 1 or 1 is 1, 1 or 1 is 1, 0 or 1 is 1, and 0 or 1 is 1, okay? So there we go, we've got 1, 1, 1, 1, exactly what we needed here, Okay, done. And we can do the same thing for the blue channel as well. Obviously, if you have something like, you might have 23 or 48, you're going to get something different, okay? And it's going to depend on what the binary was that makes this up. But for stuff like 0 or a value, it will always be a value. So if you did something like 23 or 23 or 1, for example, you would get that. Oh, sorry, let me do this properly. 23 or 0, yeah, would give you 23, okay? Because any bits that were set will remain set, okay? And then if you ever put a 1 here, then it would add bits, essentially. Like you see here, we did 0, 1, and it added bits, okay? Cool, very, very simple stuff. So now we can just simply say or G shifted left 8 or B, okay? And if we were to print this out, it gives us our assembled result, which without this stuff would look something like this, right? Which is what we started with. And if we put anything here, like 1, 2, 3, 4, 5, 6, for example, you can see that we end up with that result. Cool. So we have successfully learned about bit shifting and bit masking and the reverse of that, which is assembling everything back together. Cool. So how is this going to be useful for us in our serialization format and whatnot? So let's talk about that now quickly. So first of all, I just wanted to show you guys, in binary, this color would look something like this, right? And that's what I didn't want to draw. So you can see we've got 8 bits of 1, a bunch of zeros, and then 8 bits of 1 again. So when we do something like this red thing, then we wound up with just this. Now there are like a bunch of leading zeros, pretend, so this is like kind of a line to this side. So you can see we successfully extracted the red channel, and then of course this will actually be the same as the blue channel in this case, right? You can see these two are identical. Okay, cool. 2 things I want to cover quickly though are essentially let me just get rid of this color example, just the exclusive OR and the other thing. So if we have something like a number, exclusive OR and not is what I wanted to cover. So we have a number that's like 0x12, right? In binary, this is going to be A. In binary, this is going to look like this, right? If I were to exclusive OR something like, we had another number here, which was like 24 or something. I don't know, I'm making stuff up. And we were to, this is not going to be exclusive ORed well. I shouldn't have doubled that. Let's just say 8. That'll work well, I think, or not. 7, sure. So if we were to exclusive OR these two together, then we would actually get, so it's going to be A, and then the hat, which is above the 6 key, and then B. All right, we would basically get the reverse of that. Or rather, not the reverse of that, but we would get a 1 if they were the same. So to break this down for you quickly, because it's a bit hard to tell with the alignment, we basically had that, we ORed it with that, which of course is aligned like that, because these two are zeros. And then we got 1 0 1 0 1, right? These two, as you can see, are unique, so we got a 1. These two are not unique, so we got a 0. These two are unique, so we got a 1. 1 and 1, of course, are the same. They're not exclusive, so we got a 0. And then 0, 1, and we got a 1. Okay, there you go. That's how exclusive OR works. And it is quite useful as well. All right, finally, we have the not, which is just a squiggly line and then A. You can see what that did. It's a bit difficult to really understand what it did unless you happen to understand it, I guess. So you can see that it did actually reverse it. We did it to A. So you can see that if you copy and paste this number, you will see that the difference between these two is that it basically just flipped every bit, right? And then it added a whole bunch of 1s. The reason it did that is because we're dealing with a 32-bit integer type. So really what you had, of course, is just this. That's what this looks like in memory, okay? So those all got flipped into 1s. If you reduce the type to something like a short or a byte and you try and flip it, you'll get a smaller number. Or at least you should. Maybe not. Short. That's a bit weird. It's because it's taking in an int. So if we make it take in not an int, like a byte, for example. So it was implicitly casting over there. So this is going to yell at you, apparently. Am I printing binary? What's wrong with... Oh, it's integer to binary string as well. That's probably not great. This is going to be a bit difficult to print. But if you do something like a short, and then you maybe print it in hex. So we print that in hex. Oh, man. All right. More casting, apparently. Then you can see that we'll only get kind of those things out of it. We could probably do this with a byte, to be honest. Yeah. Still not pretty happy with that. Anyway, I guess that is, yeah. I'm not sure what it did there. Well, I actually do know what it did there. So much casting. Stop doing that. There we go. ED, right? So if we had something like, what's something that it can easily flip? F0, we'll get 0F. Or if we had 0F, rather, we might get F0. Yeah? So it just flips it. Okay? That's what not does. Cool. All right. All that aside, how can we use this in our formats? Well, this is the deal, right? It comes to us being able to convert to and from certain values. So if we have something like this, is actually I'm not going to have time to do this right now, so I'm going to have to leave this for the next episode. I didn't expect this to go for so long, and I have to get to work because it's 9 AM. Anyway, I hope you guys enjoyed this video. Next time we're going to actually take a look at how this will work in our serialization library, and we'll basically write a utils class which will implement a lot of these operations to and from binary conversion from various different data types, okay? And then we'll take a look at how that data will be represented in memory and in our actual file, okay? So if you guys enjoyed this video, please hit the like button. You can support me on patreon.com/thecherno if you enjoyed these videos and you are a super fan. Of course, don't forget to join the Slack channel, slack.thecherno.com, if you want to engage in some real-time messaging with the entire Cherno community. So thanks for watching, guys. Hit the like button if you enjoyed, and I will see you guys next time. Goodbye.